cell phone, now might be a good time to silence it. If anybody needs a restroom, they're right outside. Men's is right there, and the women's is just around the back of it. If you're interested in programs at the library and you want email notification of them in advance, you can sign up on the library's list, put your email contact, and we'll add you to the list of people that we notify. There's also a sign-up list for signs at your library if you're interested in getting notification about that or learning more about it. What else? Nothing else? So, it's my pleasure to introduce you, Dr. Sarah Stein with Hawaii Alliance for Science.
Thank you, and welcome on behalf of the Hawaii Alliance for Science. It's great to have you all here tonight. My name is Sarah Stein, and the Hawaii Alliance for Science is part of a global initiative supporting science-based communication. And we advocate to ensure that science can thrive in Hawaii, and one of our goals is to convene opportunities for science in our community. And this collaboration with the Lake Public Library has been a great way for us to do that. So that's what we're doing. We do have a couple of our board members here. We have Sarah Thompson in the back, who is the statewide coordinator for Hawaii Alliance for Science, and Jen Henry is also here. So we're very happy this evening to welcome Dr. Steve Businger. And Dr. Steve Businger is professor and chair of the Department of Atmospheric Sciences at UH Manoa. He has made notable contributions to the atmospheric sciences in several important yet diverse areas. For the past 30 years, Professor Businger has been active in researching the evolution and structure of destructive atmospheric storms, resulting in fundamental contributions to our understanding of the formation of storm systems in cold air streams and in the tropics, like Kona lows and tropical cyclones. So to date, he has over 80 peer-reviewed journal publications, published 2 academic textbooks, and 7 book chapters. Dr. Businger was elected as a fellow to the American Meteorological Society, AMS, in 2010, and he's an AMS certified consulting meteorologist. And in 2011, Professor Businger received UH Manoa Chancellor's citation for meritorious teaching. So we have a great speaker tonight. Thank you all for coming. And Dr. Businger, please come.
Well, thank you all for coming. After that marvelous introduction, maybe I should just quit while I'm ahead. So I'm going to actually pull a little bit of a bait and switch. I was supposed to talk mostly about hurricanes, but I'm going to talk about severe weather in a warming world. Actually, hurricanes are a form of severe weather, and I will talk about hurricanes today, but I'm twisting it a little bit because you all live on Kauai, and Kauai is a place that has had some particularly intense severe weather during the past year, and I'd like to touch on that a little bit. And it wasn't associated with the tropical cyclone. So I don't know if this photograph is familiar to you. You all know where this is? Somewhere up on the North Shore last April 2018. This was a flood that actually broke records. There's my name, Steve Businger, University of Hawaii. I will give a copy of this talk in a PDF form to the host this year, and she can make it available to everybody. If you have any interesting photographs that relate to this event or any other event, weather related, or any other event you want to share with me, let me know after the talk, and I'll give you my business card, and that way we can maybe connect and have you, and I can share with you as well. Okay, so severe weather in a warming world, that's what I would like to talk about. And I want to start with this because there are a lot of people who still are a little on the fence about global warming, whether it's happening or not. And this little video talks about it. I don't know whether it's got the sound turned on? It doesn't matter. If not, then I will talk it through it. This is from satellite. These are satellite images that are taken from NASA satellites. And the NASA satellites show you both the ice extent, but also the ice thickness. And so over the time that we've had these satellites, and this is, it's going to start in just a moment, going back to 1984. And so in this particular video, the white is ice that has been around for more than a year, so it's multi-year ice. The gray is the ice that forms and melts on kind of an annual basis. And you can see it doing that. So it expands during the winter, and then it melts back during the summer. So one of the things that you see is that some of the ice is coming out here between Greenland and Spitsbergen, that's part of Norway. And there's also a big area of ice that's in the Beaufort Sea here that is swirling around, and it is lasting more than a year, and that area is what we call the nursery for this older ice. So here we have 1998, and what we see in this gradual summer and winter expansion and contraction of the ice is that in recent years, starting in about 2007, there's been a marked melting back of the ice in the Beaufort Sea. And you can kind of see this is 2004. You can see it's gradually decreasing in the amount of multi-year ice that we have. And what that ends up doing is making it more susceptible to melting during the summertime. So this is 2007, and we can see that the multi-year ice is definitely decreasing. And the reason for this has to do with the fact that the ocean is becoming warmer. It turns out that most of the warming that we have been experiencing over the past 30, 40 years has been in the ocean. But the ocean has tremendous heat capacity, so the ocean temperature doesn't change a whole lot. But it does have a very large impact on what's going on in the Arctic. And this is, of course, very important strategically, because you can see that the coast of Russia is every summer melting out quite a lot. And you can see the difference between 1984 and 2016. Whoops. Anyway, so going on. So this is 2007 right here, and this is the amount of the ice extent. And you can see the variability from summer to winter used to be pretty small, but in recent years it has become very large. And that's a reflection of the fact that we are losing our multi-year ice, and now we have much larger melt happening in the summertime, and therefore the ice extent is taking on a new paradigm, if you will. This has implications for the entire northern hemisphere, which is where we live, of course, and I will talk a little bit about that. Okay, so this particular storm in April of 2018, it broke the all-time U.S. 24-hour rainfall record. So it was really an unusual storm. Not just a little bit unusual, but it's the all-time record that was broken. It happened because there was a tremendous amount of water vapor. This is a water vapor map that we're seeing right here. And this is a plume of water vapor hitting Seattle. It turns out that Seattle had 5 inches of rain associated with this particular plume of moisture. There's more moisture in one of these plumes coming up than in the Mississippi River. So there's a of circulation of moisture coming up. Here's another one. We call these atmospheric rivers. And it turns out that Kauai was in the middle of a big plume of very, very high water vapor content. In addition, there was cold air coming in aloft and a lot of thunderstorms that happened. And as we know, there was a flood that was record-breaking and very devastating for a lot of people. There were a lot of bison were hanging out on the beach after this, which is an interesting happenstance. Most of Honolulu was flooded, and for several days there was no way in and out of Honolulu because there was a landslide on the road, as you probably know, and as a result people were stuck here for 3 days. I spoke to somebody in the Big Save or little market down here in Honolulu, and she said that they used air mattresses. They blew up, and then they used towels as blankets, and that's how they survived the nights. Could be worse, but still interesting. So how much rain fell? Well, if you look at a 24-hour period, about 50 inches fell, and that maximum was in Waipa, which is just on the west side of Honolulu Bay. There's a little rain gauge there, and luckily no geckos had laid any eggs in it because it was functioning quite well. They had to check it, and the National Weather Service certified that rainfall total as being a record. For the whole storm event, there might have been closer to 60 inches. I've heard that number mentioned also, but you can see what the gradient is. At Mount Waialaeale, there was 33 inches. In Princeville, it was 15 inches. So you can see between Princeville and this location here, Waipa, there's a tremendous difference. 3 times more rain fell here. Also along the east side here, 4 inches, 3 inches, 2 inches. So it was not a uniform heavy rainfall event. It was very localized. So why was that? Why was it so localized? It turns out that the reason it was so localized is because of the terrain. That's one of the reasons anyway. This is Mount Waialaeale, and you can see that as you, this is Honolulu Bay, you can see how there's some scarps in here, and they have a certain shape to them. If you think of the northeast flow coming in, these scarps are kind of catching the flow and lifting it, and causing the thunderstorms to be more intense. And so a lot of it has to do with that feature. This is the radar total rainfall. And an interesting thing, the radar is located down here, south side of Kauai. And it's looking up over the top of Mount Waialaeale. So it is seeing the top of the storm. But even so, it's able to give an estimate of how much total rainfall fell, but it puts it in the wrong place, a little bit in the wrong place, because essentially what it's doing is it's looking up there and seeing the top of the cloud having a lot of moisture, a lot of liquid water, but there are winds that are blowing, and the wind is taking this and actually placing it over here a little bit. Now, if you were in Honolulu the night that this storm was peaking, you will recall that there was a lot of lightning. This is Kauai over here. And there's so much lightning that you can't even see the island. Here's Oahu right there. Oahu had a lot of rain the previous day. We had like 5 inches, and that fell in about an hour, and Honolulu was flooded as well. The highway was washed out, and it was a lot of problems on Oahu too, but nothing compared to Kauai. So if you look at the total lightning, turns out that, and you add it all together, this is how much lightning strikes occurred. It's a little hard to see, but the lightning pretty much is in the right place for the heaviest rainfall. So that's kind of interesting. It's not too surprising because when you think about it, if there's lightning on Kauai, it's probably going to rain somewhere, right? Lightning doesn't happen here without heavy rainfall. And so you can actually convert the lightning rate into a rainfall estimate. That's actually work that I've been involved in. The next thing I want to talk about is a different storm system that also produced some severe weather. This one occurred in February of 2019. Let me see if I can go back. And as you can see, here's Kauai, and this is Maui over here. And this storm system has a lot in common with the one that happened in April. This one is different in that it doesn't have the moisture source, so it didn't produce as much precipitation, and it didn't produce as much lightning. But it was a very intense little storm. We call this a Kona low. Look how it's coming down. It's swirling down, and it's producing a northerly flow of very cold air over Hawaii. Last February, I don't know if you have a thermometer in your yard or in your house, but you might remember that this was a particularly cold event. And I know that my wife was talking about moving to a warmer climate when this storm came by. The other thing that's interesting is, well, it produced a lot of wind. This is me on a road in Maui. If you look at the trees, they're blowing, it's about 30 to 40 knot winds with higher gusts. And of course, I should not have been driving. I mean, this is insane, right? Who would be driving on this road? As a matter of fact, there were a lot of trees down along this road. Yeah, that's me. My wife's like, what are we doing here? I said, I'm a meteorologist. You know, it's like when there's a tornado warning, I go for the roof, not the basement. So this is what it looked like. This is the low, and it's a little hard to see. Well, Hawaii is right about there. Right here where all that northerly flow is around the low, because the circulation is this direction. So we have northerly winds at the surface. The dark blue means that it was a really low pressure compared to what it normally should be, compared to climatology. And the red here is high pressure compared to what it should be. So it was higher pressure here and lower pressure there, and it produced very strong winds. And those winds, of course, created large waves. And at the summit of, this is CFHD, so this is the summit of Mauna Kea on the Big Island. The winds were over 150 miles an hour. And in fact, there was one anemometer that blew off at 194 miles an hour. The question was whether that 194 miles an hour was really accurate when the thing's about to blow away. But this one didn't blow away, and it measured a good 150 miles an hour. So it was definitely, and that's a record for the summit of Mauna Kea. So this was a record event. And I like talking about records. This was a beach in Maui before the storm, in the afternoon before the storm. And this is after the storm, so this is February 9th. February 10th. It looks like this. It's a little hard to see, but the beach is gone. All that sand got pushed away. Of course, the sand will come back, but it is interesting how much sand can be moved by a large storm system.
Which beach is that?
That is Kapa'a on Maui, right? Ka'anapali, sorry. Ka'anapali Beach. And snow was down to 200 feet on Haleakala, Maui. That's why, you know, people were talking about moving to a warmer climate. It was about, global warming, temperatures are going up, and yet you have these events that make you want to move to a warmer climate sometimes. And why is that? So I want to talk a little bit about the whole issue of climate change and show some very fundamental pictures. You've all seen this one before with the warming temperatures and the carbon dioxide. And the question is, why do they show carbon dioxide? What's important about carbon dioxide? I mean, it's in parts per million. It's not that abundant. There's not a lot of carbon dioxide in the air, parts per million. And yet, of course, the question is, where does this increase in carbon dioxide come from? It turns out it comes from fossil fuel burning. The reason we know that is because deep in the earth, you just have carbon-12. And in the atmosphere, you have cosmic rays which produce carbon-13. So if you take a bunch of carbon-12 out of the ground and put it into the atmosphere, the ratio of carbon-12 to carbon-13 is going to drop. And that's what this shows here. So as the carbon goes up in the atmosphere, the ratio of this carbon-13 is dropping because we're putting a lot of carbon-12 in the atmosphere. This is kind of a smoking gun that's, yes, we are responsible for the increase in carbon because it is, it's coming out of the ground. And there's no other place for it to come out of the ground, really. So the next question is, why do we talk about carbon dioxide? Why is carbon dioxide the important thing? Here's a graph that shows the ability to absorb radiation on this axis and how long it stays in the atmosphere on this axis. And it turns out that carbon dioxide is important because of the fact that it stays in the atmosphere so long. Another very important greenhouse gas is water vapor. And water vapor is gradually increasing too in the atmosphere along with warming the climate. And a lot of people have said, well, if water vapor is increasing, that's obviously causing the global warming, not carbon dioxide. Well, it turns out that water vapor stays in the atmosphere. If we were to put water vapor on this chart, it would stay in the atmosphere a few days because it rains out. And so it doesn't have an ability to affect climate change because it rains out. It has a residence time in the atmosphere of about 2 weeks. And so it can't cause climate change. It can help, what's the word? It can help make it more, it can increase the impact of carbon dioxide. But in and of itself, it doesn't create climate change because it just doesn't stay in the atmosphere long enough. Okay. So now what I want to do is give a little graphic. This is observations now. This is not model output. This is just observations. It starts around 1950 and it goes through 2011. And what we're looking at is the temperature collected across the entire mainland U.S. in the summertime. And you're subtracting off climatology. So what you're looking at is how far away from climate are you? This is where the climate was 0 in 1950, and this is where it is in 2011. But let's watch how this works. This is 1950. It's all right here. This is the warm weather, and this is the cold weather. And then in the 90s and in the 2000s, all of a sudden there's this shift. This is a visualization of climate change. This is interesting for a couple of things. One is that there's an awful lot of superbly hot days that are several standard deviations away from what used to be normal. There are still cold spells that are several standard deviations away from where, from the mean, where it used to be the mean. So we are still able to predict there's snow storms that allow people to take snowballs into the Senate. However, in the summertime, you can bet they're not going to be outside with their barbecue because it'll be too bloody hot. This is the same thing for Hawaii, but it's not done as nicely. But this is from 1901 to 2000, so it doesn't even go as far. It doesn't even go the last few years. And basically the blue temperatures are below normal, and the red temperatures are above normal, according to the mean from 1971 to 2000. And you can see that there is a trend. Now, how big is this trend? It's not very big. And we're just talking maybe half a degree or something. It's pretty small. Why is it so small here? Because our climate is damped by the ocean. Maybe I should have shown this before, but this basically said this is the old climate and here's our new climate. So we've gotten a little bit warmer, but the real story is over here, that we have now events that are going to be so far from what used to be the mean. And I would argue that the Kauai flood is an example of one of these. It's an example of an event that is out here in the tail that is associated with the fact that the atmosphere can hold more moisture as it gets warmer. So you still have cold days, but you have a lot more warm days. That's basically, and if you plot record highs versus record lows, you'll see that there are a lot more record highs than there are record lows. You still get record lows, but you have a lot more record highs. One of the things that is talked about in terms of climate change is that there will be more droughts, and at the same time, there will be more floods. Now, how can that be? How can you have more droughts and more floods? And this is the little graphic that I used to try to explain that. Let's say that you are near the ocean, and you have a temperature around 70 degrees. Sorry, this is in Celsius, but that's about 70 degrees Fahrenheit. And you have this much water vapor, and your relative humidity is 52%. You're near the water, and it's, you have 52% relative humidity. That's similar to what we might have in Hawaii. It's a little on the cooler side, but in the wintertime, you can have 70 degrees and 52% relative humidity. Now, if you take that same air, and you move it over, say, California, where you're away from the ocean a little ways, then you can have a temperature that's up around 90 or in the low 90s. And you have a relative humidity of 28%. This amount of water vapor is identically the same. It hasn't changed. But the fact is, it's so dry in California because you have warmed the temperature without changing the amount of water vapor that's available. So if you are away from the ocean, you will have dry conditions. If you're away from the ocean and you have warmer temperatures, you're going to have dry conditions and droughts. If you are near the ocean, on the other hand, as the ocean gets warmer, the amount of water vapor in the air depends on the sea surface temperature. So droughts result in drying of the forest, and you end up with more wildfires. And of course, it's complicated by the fact that you do have fire suppression, and then you have buildup of fuel, and then you have people moving into these fuel-rich areas. Then you end up with fires, and you really have a big problem. But I think that the bottom line is that in the western United States, there has been an increase in the number of fires associated with the drying that's happening because you have warmer temperatures without more moisture. This is predicted sea level in 2100. We might need to build some dikes in here. The Dutch are very good at that. So we might have to talk to people like at the University of Wageningen or Delft in Holland to build some dikes here. Anyway, back to the fact that the ocean is where the heat is going. So we have more carbon dioxide in the atmosphere, we have a little bit more moisture in the atmosphere, and the radiation from that back to Earth in the infrared is what is warming the planet, but most of that is going into the ocean. The ocean has a tremendous amount of heat capacity. You can put a lot of energy into the ocean, it's not going to change the temperature very much. If you want to know more about that, I can say something after. But in any case, most of it is going into the ocean. Only a couple percent going into the atmosphere. So we have climate change in the atmosphere, but it's really most of it's going into the ocean. Now that does result in a warming of the ocean. This is the temperature trend from satellite as measured by a couple of different scientific outfits here. And essentially going from 1980 to 2015, and how much warming is there? There's like 0.2 of a degree. You'd say, well, 0.2 of a degree, that's almost in the instrument noise. You know, that can't be very important. But it turns out that it does affect the amount of water vapor. So precipitable water is about how meteorologists talk about the amount of water vapor in the air. It's the total amount of water vapor in the air. If you just take it all, condense it on the ground, and then you measure that in kilograms per meter squared, which is the same as millimeters on the ground. So you can think of this as millimeters of water on the ground. There's an increase in it's a measurable increase. And these bumps here are El Nino bumps. When you have an El Nino, the ocean is warmer at the equator, south of here, and it creates a global bump in the amount of water vapor in the atmosphere. Okay, so now I want to turn and talk about hurricanes, because hurricanes derive their energy from water vapor. And notice it says down here, cumulus lit from below by California wildfires in 2018. I read that online. Yeah. And it was a total lie, because it was a graduate student from the University of Hawaii who took this photograph while flying between California and Hawaii, and this was over the Pacific. So there were no wildfires. So there is such a thing as fake news. All right? Actually, this is false news. Clouds are lit from below by the setting sun. But don't you think it just seems like a more gripping caption to say this is California wildfires? Of course. And everybody's going to send it around to all the relatives. God, look at these incredible wildfires in California. Anyway, I just thought I'd say that you got to be careful in what you read. It ain't all true. But I do want to say that I have a lot of integrity. I work very hard to make sure that what I present is accurate. And it's kind of interesting because Trump appointed a climate change denier to head NASA. It didn't take very long for him to flip, because he's a scientist too, and he just got to see all the data, and he's now a climate change believer. I don't know whether he's still at NASA. Maybe Trump will have gotten rid of him. Sorry. This is not about politics. All right, so I want to talk a little bit about hurricanes in Hawaii and how climate change might affect hurricanes in Hawaii. And then I wanted to talk about hurricanes a little bit more. This is actually a map of hurricane tracks. And it's everywhere, but it has a little bit of Monte Carlo stochastic simulation because we have not enough hurricanes around the Hawaiian Islands. So a little bit was done to give a clearer picture. But in any case, if a hurricane passes within 75 nautical miles per 10 years, then it'll be counted in this map, and then that's what these numbers over here.
75 miles of what?
Of a point.
Hawaii?
Latitude, longitude intersection lines. So at 75 miles from latitude, longitude crosses. And what it says essentially is that this area here there's a tremendous amount of hurricanes right here. They form every year there. A lot of them spin off into Baja California. A lot of them just spin to the north. None of them ever make it to Los Angeles, even though there's so many hurricanes here. They never make it to Los Angeles because the water's too cold. And so the storm dies. Very few make it out here into the central Pacific, and when they do, they tend to fly to the south of the Hawaiian Islands. And if they try to go further north, they're buffeted by bad winds and cooler sea surface temperatures, so Hawaii is pretty happy. But hurricanes, it turns out, are gradually moving away from the equator in both hemispheres. Every year, they're just inching a little bit further from the equator in their tracks. And so the models are showing that, projecting for 2075, that we will get about 2 more hurricanes in this area right here. And we'll get less hurricanes down there. So this is sort of a climate model shift in hurricane tracks. That's the expectation. But maybe the hurricane will blow the volcano out. That slide is actually from last year, where Kilauea was going crazy, and we had Hurricane Lane that was coming in, and so they were thinking, well, maybe. Hurricanes have their beauty too, and so that's where this little title comes from, the beauty and terror of hurricanes. I like comparing this satellite map, which is from 2015, to this Starry Night from Vincent van Gogh, a famous Dutch painter. You know, he never made any money while he was alive. And I don't know if he saw any hurricanes either. But he did lose an ear. Not to a hurricane, no. Well, that could be. We can talk about that after. So this is a hurricane that actually, Hurricane Irma. And I just wanted to show it because it has a nice high resolution, both in time and in space, animation of what this hurricane is doing. You can kind of see the deeper convection, you can see the eye there. So it's kind of a nice little animation. And here we have another nice shot of a hurricane. You can see the eye right there, and you can see the higher, deeper clouds in here, and also some deeper clouds on the outside. You know, some of these ones that are poking out in the periphery of the storm, they can actually produce tornadoes. So hurricanes can produce tornadoes, which is not a happy thought when you think about it. You think hurricanes are bad enough as it is. And then the hurricane misses, it's not going to hit you, but a tornado comes and hits you. So it could be that. The point of this slide is to show that hurricanes are rather small compared to mid-latitude cyclones. This is a cold front and a storm. And that's true for coronal lows too. You can have very large coronal lows affect all of the Hawaiian Islands at once. Whereas Hurricane Iniki hit Hawaii, and Oahu got just a few waves. So hurricanes tend to be very, very surgical in how they affect the populations. And this slide here shows how flat hurricanes are. They're much, much broader than they are tall. They can be 500 miles across in terms of their shield, and only maybe 15 or 10 miles maybe deep. So not very deep, 16 kilometers, maybe 10 miles deep. And this might be 300 miles. Of course, the eye is much, much smaller. The eye typically is maybe 30 miles in diameter, the average hurricane, but it may be less. And that's where most of the action is, right here where the eye wall is. And then there are these bands on the outside. Like I said, sometimes you can have a tornado associated with some of those spiral bands. So this is typical for a hurricane. You've got spiral bands, and then you've got this symmetric eye wall in the middle, and a clear eye in the center because air is actually coming down in the eye. The other interesting thing about hurricanes is the winds actually decrease with altitude. That's not true at a coastal low. Coastal low, the wind speeds increase with height. That's why Mauna Kea had 150 mile an hour winds, but we only had 40 mile an hour winds at the surface. So, unlike a coastal low, the hurricane weakens with height, but the strongest winds are right near the surface, which of course is not a happy thing, because that's where we are. You can tell how strong a storm is by the colors, by how cold it is, and that's given by the color here. And the folks at NOAA and NASA, they choose pretty colors to make the storms look interesting. This one here had 215 mile an hour winds, and it hit Mexico back in, I think it was 2015. Yeah, 2015. So here are some different storms: 195, 155, 160, 180. So depending on how strong they are, they have a different look. And that's important because if you don't have an airplane flying through the storm, you can tell something about how strong it is by looking at the satellite data, and that's exactly what the forecasters do. So what do you need in order to get a hurricane? You need to have warm ocean water. Temperature has to be about 80 degrees Fahrenheit. If it's not that warm, you probably won't get a hurricane. So the sea surface temperature is critical. That's why with climate change and warmer oceans, we have something to think about. Could be a problem. You need to have some kind of pre-existing disturbance. There has to be something, a low pressure area that you're going to use to concentrate the winds. Then you need to have thunderstorms, and you need to have little wind shear. Now that's a happy thing for Hawaii because we have a lot of wind shear in Hawaii. We tend to have a Hadley circulation here with strong southwesterlies aloft and northeast trades at the surface, and that takes the storm and just shears it off, and that's what happened with Lane, wind shear. And then you have to be away from the equator because you need the spin of the Earth. Now you need to have lots of water vapor, and that's the driving force for hurricanes. This is showing saturation vapor pressure as a function of temperature, and you can see that it's exponential. So if you get here to 26, you're right there. And if you're colder than that, then you don't have enough water vapor. So the sea surface temperature determines how much water vapor you have. And you can see that on this little chart. And this exponential curve is that makes the difference between having a hurricane or not having a hurricane. It's this, you need to be right about here. And the ocean doesn't get much warmer than 30. So the difference between right here and right there, 26 and 30 degrees Celsius, sorry, I should switch those to Fahrenheit. The difference between about 80 degrees Fahrenheit and about 86 degrees Fahrenheit or 88 degrees Fahrenheit makes the difference between a Category 1 hurricane and a Category 5 hurricane. Very small difference in sea surface temperature. So the sea surface inching up, and then you have these anomalous areas of warm sea surface temperature during El Nino. You can see how this could create a problem for us. And this is sort of saying the same thing. This is the sea surface temperature. The warmest sea surface temperature is over here, near New Guinea. Also, there's some warm sea surface temperature here, and also in the Gulf of Mexico. And then you have to be away from the equator. And the warmest sea surface temperature results in the lowest surface pressure of the storms. These numbers up here are the surface pressure of the typhoons. Typhoons and hurricanes are the same thing. And you can see they're in the 870 millibar range. And over here, they're 880s. And so sea surface temperature and the intensity of the hurricane are directly related. It's not to say that if you have warm water, you're always going to get a hurricane that's really intense. That's not the case. But if you don't have warm water, you won't get a hurricane that's really intense. So it's a requirement, but it's not sufficient. So here are the tracks. There you can see the area hotspot to the east of us. And then this is the Westpac, and that's, right in here is the Philippines. The Philippines is right in the middle of where all these typhoons go. And again, typhoons and hurricanes are the same. Australia has a lot of they call them cyclones down there, and they call them cyclones in India too. Quite a few in the Gulf of Bengal. So we had quite a bumper crop in 2018, and I want to talk a little bit about why that was, why we had so many. But first, since we're on Kauai, I thought I would just go down memory lane and talk just for a moment about Hurricane Iniki. It happened in 1992. I moved to Hawaii a year after, and I remember coming to Kauai and seeing all of the Norfolk pine trees had lost their branches across most of the island. It was really quite remarkable. But, well, I should say, this house and this house are the same. It was really destroyed. And this is the track of Hurricane Iniki, and this was the area of storm surge right here. You can see that the track to the right of the track is where the winds are the strongest. To the left of the track, you have to subtract the winds from the motion. So the winds are a lot less strong on this side, and they're a lot stronger on that side. Okay, so that's where the storm surge was. Then you also have to worry about things like flooding. And this is about 90% of the structures were affected. A lot of them were destroyed. 30% of all the telephone poles on the island were knocked down. And there was quite a storm surge. Now, what is a storm surge? It's actually where you have the ocean rises up higher than the normal tide. So if you have a normal tide here, this would be the storm surge, the difference between here and there. That's the storm surge. And on top of the storm surge are the waves. So the storm surge is not the waves, but the waves are on top of the storm surge. So the storm surge is essentially just a raising of the tide. So the whole ocean lifts up, and part of that is because of the low pressure, and part of that is because of the winds are causing the water to bunch up. Here is the high water mark after Iniki. It took all of the houses that were over here, broke them into little bits, and took all the furniture and left it in a line right up here, about a quarter of a mile from the beach. This is what would happen if you had an Iki hit Honolulu. There was a thought at the time that an Iki might hit Honolulu if it had, instead of hitting Kauai. This is where the water line would be, and we would have had a mess in Honolulu for sure. This is kind of showing one of the condos and some of the debris from the storm surge. So, weather forecasting helps, and so in the old days, before we had good weather forecasting, we had a lot of fatalities because people would go swimming just as the hurricane was hitting, or they would think that the hurricane was over when the high came over, and they said, oh, it's over, and they would run out into the ocean, and then the other half of the storm would hit. So there were a lot of fatalities here. Of course, the biggest one was Galveston. We had a bit of a problem politically because we decided not to talk to Cuba. And the Galveston storm came from Cuba. Cuba knew that there was a hurricane, and they tried to communicate that to the United States, but the United States wasn't listening. There's a book about this. In any case, it's good for weather forecasting to have open data communication. We get data from Russia and China, and we give them data. We have open data communication, and it's very important for forecasting. Anyway, in the early days, a lot more fatalities, and in the later days, you have a lot more loss of property and less fatalities, but still, Katrina produced a lot of fatalities, mostly people drowning. Michael in 2018 was very devastating, a very, very strong storm. And it's interesting to see, this is where Michael went, and this is how much development there was in 1970. There wasn't that much development, but if we go forward in time to 1990, you can see there's more population on the coast by color. This is 2018, a lot more. And you can see that the coast is much more built up, and that's why we have a lot more. People like to live near the ocean, and we have a lot more property damage as a result. We have less loss of life because people tend to they listen to the National Weather Service forecasts, which are getting better. Harvey was a very devastating storm because it produced so much rain, kind of like the flood in Kauai, but much more widespread. And this is Houston. You can see that they had a bit of a problem. Houston, we have a problem. So, Hurricane Sandy was an interesting storm, and it also created a lot of problems. It came over a very warm sea surface anomaly, and it maintained its strength, similar to Harvey. Harvey strengthened as it approached the coast, and there was hot water in the Gulf at the time. The subway flooded. This is the subway system. The Jersey Shore was inundated with a big storm surge. This is Brooklyn. Manhattan was flooded. It was a really devastating storm. So if you think about these storms, they're becoming more expensive. Harvey, they say, was $190 billion worth of damage. And of course, these numbers tend to go up because it takes a while for their insurance to kick in. And then Katrina is second. Sandy was third. Andrew was a pretty bad storm. And then you have to go through down here. I think that Niki would be right here at about 10 billion. So in 2018, we had a lot of storms. You can see Hawaii is right here. This one is Lane. It came up and did a turn. And the reason there was so many storms in 2018 is because we had such hot water over here. And that's because it was still kind of a leftover from El Nino that we had in 2015-16. So Lane was quite the storm. It came up Category 5, really close to the Hawaiian Islands, and it was forecast by the models to run straight into Maui. That's where it was going. But the Weather Service was smart enough to realize that there was wind shear that was going to take the top off of the storm, and at that point, the northeast trades were going to take it in this direction, and that's exactly what happened. So the Weather Service did an excellent job of forecasting the storm. Huge high winds out in the ocean. This is in knots, so it's over 100 knots at a buoy. And then the buoy, of course, just lost its instrumentation when it got to that wind speed. The biggest impact from Lane was on the Big Island. It had very heavy rains that lasted about 3 days and produced a lot of flooding. So here's the 40 inches of rain. It's not the same as 50 inches in 24 hours, but nevertheless, it produced a lot of flooding for the Big Island. And that flooding inundated a lot of Hilo and produced landslides and a lot of damage. So Lane was a forecast bust for Honolulu. They were expecting all kinds of big waves and wind, and absolutely nothing happened. And I think Kauai had the same thing. In other words, the possibility that Kauai was going to see winds and various impacts, but nothing happened. Thank goodness. All right, so I have more that I could say, but I want to keep people from falling asleep. So this photograph I took last night over at the Overlook. You know, I know where it is, down on LA. And I would say Kauai still has that magic. It's a fabulously beautiful place. So, yes.
So, would you like to predict what direction the hurricanes would be hitting Kauai from? Are they going to come up from the south like Aniki or some other direction?
Well, if the hurricane tracks gradually shift northward, and then the Big Island gets more and more in line with where the hurricanes are going, the Big Island, it turns out, will not cause hurricanes to deviate much, but if a hurricane makes landfall on the Big Island, it'll knock the stuffing out of the hurricane and completely protect Kauai. So that's a nice thing. However, it is true that hurricanes often slide just to the south of the Big Island. The islands themselves form a bit of a barrier to the northeast trade winds. So the hurricane actually has a tendency to kind of want to curve up and hit Kauai. And I think that's one of the reasons why Kauai has had several hurricanes in the past. It was Todd in 50, there was Eva in 1982, and there was Aniki in 1992. And here we are in 2019, and Aniki, Kauai has not seen a hurricane since Aniki. Now that's a bad one, as far as unless I'm missing something. So what's going on? I don't know. I would say that there's two possibilities. One is that the storm can go just to the north of the Big Island and hit Kauai. That's a possibility. The temperatures are cooler to the north, so it probably won't be a super devastating storm. The most devastating storm is going to come from the south because it's over warmer water, then it turns. But in order to turn, it has to have it follows the mean wind. It needs to have some kind of a mean wind to do that, and that's unusual. So it's not a high probability event. And I'm not certainly predicting it. I still think y'all, if you own a house, put some hurricane clips on the roof. Keep the roof on the house, because then your furniture stays dry. And if you lose your roof, other people are going to lose their roofs, and there's not going to be anyone to put a new roof on, because all the carpenters will be already engaged helping their friends or they will have moved to a different state because they don't like Hawaii after a hurricane. So the best thing is to make sure that your house is properly protected from hurricanes. Yes?
When you showed the Navy, you showed where the winds were stronger on the east side and the west side. Is that because the storm is going counterclockwise?
Yes.
Is that the reason for the stronger wind on the right?
Yeah, that's because on the right side of the storm, which would be the east side if you're moving north, the storm motion and the winds are in the same direction, and it turns out you add the two together. On the other side, you're subtracting the storm motion from the wind speed, and so there's a big difference, plus the storm motion on one side minus the storm motion on the other. And you end up with a very focused, very strong wind on just to the right of the track in the eyewall. So it's almost like a tornado. It's very narrow and it's very surgical. And that's why hurricanes can come close to the Hawaiian Islands and we all go, oh, that was nice, but nothing happens because they're so small in their area of hazard. But it only takes one.
And what would be the difference in miles per hour or knots of, say, to the right side of the storm to the left side where it's going down?
Well, Iniki was moving, depends on the storm motion. So some hurricanes move slow and some move fast. So the difference can be a lot. In Iniki's case, it was moving at 30 miles an hour. So on one side, you had 90 plus 30 is 120 mile an hour winds, and on the other side you had 90 minus 30 with 60 mile an hour winds. So essentially from one side to the other, doubled from 60 to 120. Yeah.
So for the students in the audience, what do you see as the best opportunities career-wise?
If you're interested in environmental science, the University of Hawaii has one of the world's strongest programs in geosciences. And we have a major called Global Environmental Science that you can enter as an undergraduate student, and you get instruction from professors that are really top-notch. So where I think that the oceanography program was in the top 10 in the world in several recent surveys, and that's out of thousands of universities, thousands of programs. So it's a real stellar program. So I think, thank you for asking.
It's a fascinating subject.
Yeah. And we have a good atmospheric sciences program, and so, yeah.
What do you think would happen if Yellowstone erupted?
If
Yellowstone erupted.
Oh, wow, that would be really interesting. Yellowstone is a mega volcano, and it would spew a lot of stuff into the atmosphere, and it would probably result in cooling of the atmosphere for several years. Yeah, could be interesting. Not real likely within our lifetimes, but yes.
So I heard hurricanes referred to as heat engines.
Yes.
But does that heat engine require that the atmosphere be significantly cooler than the water? What if they're both the same temperature? Would it still work?
It's an excellent question. What is meant by a heat engine is that you have a hot temperature in one location and a cold temperature in the other, and that you're extracting energy out of that temperature difference. In this case, the ocean surface is the hot temperature, and the top of the troposphere is the cold temperature. So the ocean surface might be 80 degrees, and the top of the hurricane might be minus 80 degrees. So there's a really big temperature change in that. And that's where the energy is extracted and you can calculate an efficiency. And it turns out that the upper atmosphere has kind of a pretty uniform temperature, and therefore it is the sea surface temperature that determines how strong a hurricane can become theoretically. And that's what I showed in that one diagram. I said that the pressures are going to be lower and the wind stronger if you have warmer sea surface temperatures. And it's very sensitive to the sea surface temperature.
But is the troposphere not warming like the rest of the planet?
It's actually the top of the troposphere and the lower stratosphere is expected to cool a little bit. It's cooling. So that thunderstorms become a little stronger. Nobody's going to ask about what to do about global warming? Good. Yes.
What can we do about global warming?
Ride a bicycle, eat less meat, fly less, and if you can, afford some solar panels or an electric car. Those are all good suggestions. But yeah, and then on top of it, be careful who you vote for. You know, you want to vote for somebody who's got some grasp on reality and whose salary is not tied to making the situation worse. It's very difficult to talk someone into believing in global warming if their salary is predicated on not believing it.
Or just ignore it.
Sorry?
Or, sorry.
Or you can just ignore it. Yeah, yeah. Now, I want to just say, yeah, go ahead.
I'm just curious, do you spend time presenting this information to city planners? I mean, how much work do you do with the people that are making decisions about where the infrastructure goes? Because it seems to me like in addition to sea level rise, this would be another rare case for changing the way it's done in our community.
Yeah, you know, I think we're lucky to live in Hawaii. I think that our elected officials here are pretty forward thinking, and they, you know, I definitely spend time talking to them, but they already know what I have to say. So that's a really positive thing. I want to add also a positive note. I'm not so worried in the long run about global warming because I think we will find a technical solution to this. And the reason I say that is that we're pretty close to getting fusion energy to work, for example. Fusion energy takes helium and hydrogen and fuses it together to produce lithium. Lithium is used in electric car batteries. There's very little radiation that results from fusion. It's clean relative to fission, which is the old-fashioned nuclear energy. So fusion, if we can make it work, will allow us to have almost an infinite amount of energy, and we can use that energy to take CO2 out of the atmosphere. The other thing that's true, and that you should all think about, is that the very, very best way to get carbon out of the atmosphere is trees. Trees are very efficient at taking carbon dioxide out of the atmosphere. We need to plant trees. If you plant 15 trees each year, you can travel on jets, and you can drive an inefficient truck, you can continue your lifestyle as long as you plant trees. So that's a plug for planting trees.
Would albesias be good ones?
Sorry?
Would albesias be good ones for hurricanes in Kauai?
Well, albesias are a fast-growing tree.
Take down lots of
They
carbon dioxide.
take a lot of carbon dioxide out. You just don't want to have one in your backyard. Because albesia trees, because they grow fast, they tend to be kind of a weedy tree, and when the wind blows, stronger than about 40 knots, they start to fall down, which is what happened on the Big Island with a recent tropical cyclone that went into Puna and blew down all the Albizia trees. Is that why you asked about Albizia trees?
Yeah.
There are better trees to plant than Albizia trees. Yes. Any other questions? Yes.
At what altitude do the hurricane hunters fly into a hurricane?
That's a fun question. 10,000 feet, which is about halfway in the hurricane. And you know, they used to fly down low, but several planes lost engines as they were flying through, and then they decided, you know, they wanted to have a little bit more measure of safety. So now 10,000 feet is where they fly through. And it's pretty calm at that altitude. Every once in a while it gets a little bumpy, but not bad. It can be a really smooth ride if you're lucky. Which you wouldn't think. I've also experienced it where the engine quit working, and then you look out and the pilot's telling the other pilot, hey, I sure hope that engine doesn't catch fire. And I'm thinking, oh, let's just get home. Anyway, I send my students now.
Do they run into tornadoes when they're flying through?
They have radars on board these Hurricane Hunter aircraft, and they now will avoid the heat convection because they know that it's coming.
Awesome, well, thank you. Thank you all for coming. If people have any questions, I'm sure the doc will answer them.
Yeah, I'm happy to talk to you, and if you want a copy of my card, I'm going to
Thank you.
Thank